You ever stop and think, what can a computer actually do? And I don't just mean your laptop or your phone, I mean any computer, in theory. What are the fundamental rules of the game they're all playing? Well, we're going to dive right into that and explore the absolute, rock-solid limits of computation. So here's the plan. We're basically going to climb this ladder of complexity. We'll start with the simplest little machine you can imagine, then we'll keep adding power, and finally, we'll connect it all back to the real world. You know, the actual code you might be writing every day. And this all boils down to one huge question. And look, this isn't about how fast your processor is or how much RAM you have. It's way deeper than that. The real question is, are there some problems out there that are just impossible for any computer to solve? Like, ever? Let's find out. Okay, first things first. Before we can even talk about limits, we gotta know the rules of the game, right? And there's a whole field of study for this. It's called computability.
So, what on earth is computability? Well, to put it simply, it's all about figuring out which problems can be solved by a computer following a set of instructions. It's the study that draws that hard line in the sand between what's possible and what's, well, completely impossible.
All right, let's do this. We're starting at the very bottom of that ladder of complexity I mentioned. This is the simplest model of a computer you can possibly dream up. Let me introduce you to the finite automaton. The easiest way to think about this thing, just picture a machine with really, really bad short-term memory. So bad, in fact, that it can only remember one single thing, the state it's in right now. No memory of the past, just this very moment. That, in a nutshell, is a finite automaton.
Okay, let's pop the hood on this thing. It's got a set number of states, you can think of them like on or off, and it has this little reading head that just plods along, one symbol at a time. But the most important part, the absolute key, is that it has zero extra memory. None. And that simplicity, it's both its greatest strength and its biggest weakness. So you're probably thinking, what can a machine with no memory even do? Well, it turns out it's a rock star at simple pattern matching. It can easily tell if a bunch of ones is an even or odd number. It can check if a word starts with ab. And here's where it gets real. This is perfect for things like validating an email address format. Pretty useful for such a simple machine, right?
Now, these little machines actually come in two flavors. You've got the deterministic kind, the DFA, which is super predictable. Its next move is always a sure thing. Then there's the non-deterministic one, the NFA, which can kind of explore multiple paths at once. But here's the kicker, and this is really cool. Even though they work differently, they have the exact same amount of power. They can solve the exact same set of problems. Okay, so that whole no memory thing, it's a huge problem when you want to do more complex stuff. So, it's time to climb up to the next rung on our ladder. Let's give our little machine a memory upgrade. And this memory upgrade, it comes in the form of something called a stack. And honestly, the best way to picture a stack is to think about a pile of plates at a buffet. You can add a new plate to the top, right? And you can take the top plate off. But you can't just yank one out from the middle of the pile. That's it. That's a stack. And those two simple moves, putting a plate on and taking one off, they have official names. Push is when you add an item to the top. Pop is when you take the top item off. It's a last-in, first-out system. And believe it or not, this simple little memory structure is incredibly powerful. So what new superpowers does our machine get with this stock memory? Well, now it can solve problems the old finite automaton couldn't even dream of. Like, for instance, checking for balanced parentheses in your code. It sees an opening bracket, it pushes it onto the stack. Sees a closing one, it pops the last one off. If the stack is empty when you're done, you're golden. This is absolutely critical for understanding the structure of pretty much any programming language.
Okay, so we've given our machine a basic memory. But now it's time to go all the way. We're climbing to the very top of the ladder to meet the granddaddy of them all, the most powerful model of computation ever thought up, the Turing Machine.
And the Turing Machine is like beautifully simple. All it has is a tape. Think of it like an infinite roll of paper, and a little head that can read what's on the tape, write something new, and move left or right. That's it. But that idea of an infinite tape, of unlimited memory, that's the whole secret sauce. It means this theoretical machine can run any algorithm you could possibly write. It's the universal blueprint for a computer.
But, and this is a huge but, even this all-powerful machine has limits. And this brings us to one of the most famous, most mind-bending problems in all of computer science, the halting problem.
It asks a pretty simple question. Can you create one program that can look at any other program and tell you for sure if it will eventually stop running or just loop forever? And the answer, which is just shocking, is no, you can't. It's been mathematically proven to be unsolvable.
So this weird limitation actually splits problems into two different camps. On one side, you have recursive problems. For these, the Turing machine is like a perfect judge. It's guaranteed to stop and give you a solid yes or no. But then you have recursively enumerable problems. Here, the machine is more like a detective. It'll definitely stop and tell you yes if it finds the answer. But if the answer is no, well, it might just keep searching forever, never able to be 100% sure.
Okay, I know, this has all been super theoretical, right? You're probably wondering, what does any of this have to do with my day-to-day coding? Well, as it turns out, everything. These abstract ideas are literally the engine running inside every single modern compiler.
Think about it. When a compiler first scans your code, that first pass is called lexical analysis. And what does it use? A finite automaton. It's just looking for simple patterns, like keywords and variables. Then, for the next step, syntax analysis, it whips out a pushdown automaton to make sure the structure is correct. You know, checking that all your parentheses and brackets match up. It's our entire theoretical ladder, right there in action every time you compile.
So let's just recap our whole journey here. We started at the bottom with the no-memory finite automaton, which was great for simple patterns. Then we bolted on a stack and got the pushdown automaton, which could handle all that nested stuff. And finally, we reached the top with the Turing machine, whose infinite tape lets it handle any computable problem at all. You see the pattern, right? Each little upgrade in memory gave us a massive leap in power. So look, if you take away just one thing from all this, let it be this. The finite automaton? That's your simple pattern matcher, kind of like a basic calculator. The pushdown automaton? That's for nested patterns, like a calculator that has a memory button. And the Turing machine? That's the whole shebang. It's the blueprint for a full computer, able to solve any problem that can be solved. Period. So we've seen that even our most powerful, most perfect theoretical computer can't solve everything. The halting problem is just the tip of the iceberg. And that really makes you wonder, doesn't it? What other huge questions out there, in science, in math, maybe even in philosophy, are just fundamentally unsolvable? What problems will be forever beyond the reach of any machine we could ever hope to build?